All right, so again, this is a simulation from the same group that did another simulation that I showed earlier, and this is what we call the um, PHET website. So it's the Physics Education Research Group at University of Colorado at Boulder. So you can take a look. There's actually quite a lot of um, fun and interesting simulation that you can try, and that's very convenient because like we cannot do some of these in the lab, right? So the simulation kind of helps by a lot. All right, so anyway, what do we have here? Well, let me just introduce things one by one. So we have a speaker, and the speaker is gonna give out sound wave. So I can tap and it gonna generate sound like this. So the sound wave is longitudinal wave, right? So in a sense, the uh, black and white stripe here is indicate the wave, which can be again thought of as the compression wave or the pressure wave or the displacement wave of the air molecules. Okay, so either way is fine, but just in general, it describes some kind of the displacement of the medium. All right, so it's the sound wave coming out, but it doesn't have to be sound wave. Actually, it can be any other wave. For example, well, here you can replace this as you know a water wave, and the wave source is just a drop of water on the water surface, or you can use like light wave that looks like this. That is also fine. So it's pretty generic situation where you have the wave source and it's giving out wave. And the point that it's giving out wave is here, right? It's at the speaker. So that's what we call the wave source. And you can see that the wave is going everywhere. I'm not sure if I can move. Okay, I can't. Um, I'm, I was trying to move the speaker around maybe to the center of the screen, but it doesn't let me do that. That's fine. So what I have here is the detector. Okay, so for the case of sound waves might be our ears or something like that. And the cool thing about this is we have two probes, the dark one and the light one, dark gray and the light gray. So let's put in one at a time. So the probe gonna determine the wave amplitude at the point of the probe. And you can see that it's plotting that with respect to time in the horizontal axis, right? So what we are trying to show here, well, the probe is picking up the wave at just that particular point. So essentially what it's showing is the displacement of the air molecule at the location of the probe. And you can see that it's going up and down. So it's moving like a simple harmonic motion, just like what we talked about, a few lectures back. And you can see, well, we can demonstrate a few concepts that we talked about earlier. So if I move closer, right, you can see the amplitude gets larger. If I move away, you can see that the amplitude is lower, right? And this is because this wave is going out in every direction, right? So the power or the energy of the wave is spread out. So that's why the further away you are, the lower the amplitude. Okay, so that's probably something that you expect already. In any case, let's put in another probe here. So I'm gonna move uh, the 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 dark probe there. I'm gonna move the light probe somewhere also here. Okay, and now you can see that we have two graphs showing at the same time. And what we see is that when the dark graph goes up, the light one also goes up. And when the dark graph comes down, the light one also coming down, right? So it's going up and coming down at the same time. This is a case where we say that the 2 point, the dark point and the light point here, they have the same phase. Okay, same phase means going up and coming down at the same time. And why that's the case? Well, it's because, roughly speaking, the distance from the speaker to each probe, they are pretty much the same. Okay. But what happens if I move the light one a little bit further away? So just to make it clear, let's make them in the same kind of line of sight to the speaker. If I move the light probe a little bit away, let's say here, you can see that when the dark one is going up, the light one is not necessarily at the top anymore, right? Actually, it's almost kind of like the opposite, right? So if I move it something like this, or maybe here, how do I? Okay, maybe something like this. So you can see that the dark graph, when it's up at the maximum, the light one is actually at the minimum, right? And this is not in phase because they are not going up and down at the same time. Actually, they are going in the opposite direction, right? So this is what we call like out of phase, because when one is going up, the other one is coming down, right? And what did I change? The only thing that I changed is the distance from the probe to the source, right? So depending on how far away you are from the source, then the phase of the wave observed at that particular point will change, right? So in that case, well, in this case, the light one is out of phase from the dark graph here. But if I move further away, even more, then you can see that the two graphs now becomes in phase again, because they go up and down at the same time. Even though the amplitude is a little bit different because the light one is further away from the source compared to the dark one. Well, that's kind of nothing we can do about that, right? And then if you move further away, then it becomes out of phase again and then become in phase again, right? So if you move it such that they are the same distance from the source like this, I'm trying to make sure that they are as close as possible. Something like this. Maybe, okay, something like this. Then they are in phase again, and that's because, roughly speaking, the distance between each probe to the source are the same, right? So I can see that depending on the distance from the source to the probe, they can be either in phase or out of phase. So we are trying to describe like the condition, why that's the case, or why it's in phase or why that's out of phase, right? And why are we interested in this? Because this same principle gonna apply to the case where we have more than just one source. Because you're gonna see what we call the superposition principle, which is combining wave coming from multiple sources. So we do that by just adding them together. And sometimes the wave that you have, they are in phase so that you have what we call the constructive interference. So the wave adds up. So you have like higher amplitude of the wave. Or the two waves that you add up can be out of phase. So one going up, the other one coming down. So you always cancel each other out. And that's what we call destructive interference, right? And this simulation, actually, we can take a look at that case. So we need to go to the next one here, right? So in this case, we have not just one source of wave, but we have two of them. So let's turn on one first. And this is kind of the same as what we had in the previous page. So now if we look at, one thing which I just realized, you can see the Doppler effect in this case, right? So if I don't move the observer, that's the wave that you see, okay? But then now if I move the observer in, you can see that the frequency becomes faster. So that's the Doppler effect that we just talked about, okay? So you can see it here also. Anyway, so let's move it roughly here. Okay, so the wave we are seeing is coming from the top speaker, right, and going like this. Now if I stop the top one and then I turn on the bottom one, now the wave I see is the wave coming from the bottom speaker. Now what happens if I turn on both at the same time? Well, now the wave that I see is a combine between the two waves, one from the top and one from the bottom. And because the distance from the probe to each speaker are the same, so the wave coming from each speaker is always in phase. They go up at the same time and they come down at the same time. So the wave, which is a combination of the two, becomes larger because what we have here is constructive interference. Okay, but on the other hand, if I move it somewhere, not in the middle, maybe somewhere here, you can see that the resulting wave becomes really small. And well, if I choose it correctly, I can actually make it as arbitrarily close to 0 as I want, but it's pretty hard to do. Okay, maybe that's the best I can do. So that's a pretty small wave. If I turn off one, the wave becomes large again because now it's just a wave coming from the bottom speaker. If I turn off the bottom one and turn on the top one, the wave is large again. Okay, but now if I turn on both of them, the wave becomes small, right? And the reason is because we are combining two waves together, one from the top and one from the bottom. And the distance from the probe to each speaker, now they're not the same, right? And the phase of the wave depends on how far away you are from the source, right? So I position it such that the wave from the bottom and the wave from the top makes the two waves actually out of phase, meaning that when one is going up, the other one is going down. So it's always cancel each other out. Okay, and you can see that if you look at the pattern that is coming out, you see that's kind of like the line going this way. That's the line where the amplitude is really small. So along that line, we have what we call the destructive interference. So the two waves from both speakers kind of cancel out. But then you have, like in the middle here, what we call the constructive interference. So the wave from the two speakers actually adds up. Okay, so we're gonna look at the condition kind of mathematically, like which point can be constructive, which point can be destructive. Okay, so that's gonna be what we talk about for the remaining of this lecture. All right, so I'm gonna switch back to the lecture note here. And before we talk about the interference, we need to introduce a few concepts. And the first one we're going to talk about is the concept of phase. And what is the phase? Well, the phase is kind of like the thing that we use to say what is the kind of the starting point of the wave. So if you remember, when we talk about wave in general, we use let's say sinusoidal wave. So we have y of x and t, and that's going to be a, let's say sine kx minus omega t, right? So k gives you the information about wavelength, and then omega gives you the information about the frequency, right? So if you plot this, you're going to have at any snapshot in time, so let's say t equal to 0, the wave going to look like a sine wave, like this. Okay, and what can happen is that you have another wave, and then at the same time, at t equal to 0, the wave might be a little bit displaced in the sense that it does not start at the 0 point. Maybe it starts at the top point like this. Right. But everything else is the same, meaning that it's the same frequency and it's the same wavelength. The only difference is the starting point here. So this should remind you of the phase, initial phase that we talk about when we talk about the simple harmonic motion, right? So how do we describe that? Well, just to be more general, what you can do is you add an arbitrary phase to the argument of your sine function. And we normally take this to be 0 because not most of the time it doesn't really matter. So this is the phase. Okay, so we can take it to 0 again because most of the time it doesn't change anything that we are trying to do. But if you have like more than one wave, this becomes kind of important because it's gonna determine like how the resulting wave gonna be when you're trying to add the two together, right? So if you have, in this case, the blue wave, let's call it y1. So y1 is the blue wave. Let's say it's a sine kx, well, minus omega t, but in this case 0 because t is equal to 0, but I'm gonna leave it in like this. And then what is y2? The only difference between y1 and y2 is y2, which is the red one, is just y1 moved to the left. Right, that's the only thing that's happening here. And what does shifting the graph to the left means in terms of mathematics? It means that you add something to it, right? So you add some kind of phase here. Right. Remember, if you want to move the graph to the right, then you need to subtract. If you want to move the graph to the left, then you need to add. So in this case, the red one is kind of like moving the blue one to the left. So you got to add, right? So this is what we can do here. So this is the phase of the red one. The phase of the blue one, well, it's like 0 here, but it doesn't mean it doesn't have a phase. It's just the initial phase is 0. Because it's 0, we just don't write it down, right? But the only thing is not the absolute phase. I should say that the important thing is not the absolute phase of the two waves. It's the relative or the difference in the phase, right? So in this case, the phase difference is just phi because this is 0. Maybe I should just write it. Plus 0 like this. So you take this phase and then you subtract by that one, and that's your phase difference. So in this case, it's phi. Okay. So the phase difference is going to tell you whether the two waves are in phase or out of phase. So that's the term that we're going to hear quite a few times. So when you say that two waves are in phase, that means the phase difference. By the way, I should be more specific. The phase difference, I would say delta phi, in this case, equal to phi. Okay, so it's the difference between that and that one. So if you have phi 1 and then you have phi 2, then the phase difference is phi 1 minus phi 2 or something like that. Okay. So if the two waves are in phase, that means the phase difference is 0. That's what we mean by in phase. So that means in terms of the graph, the two waves exactly overlap each other like this. Okay, on top of each other, exactly. So when they goes up together. When they go down together. So that's what we call in phase. So opposite of in phase is what we call out of phase. So when the two waves are out of phase, the phase difference is pi or 180 degrees if you want to use degrees. Okay, so in terms of the graph, it's going to be one wave going like that, the other one going the opposite like that. Okay, and you can see that this is going to be the case when you put phi here to be pi. Okay, and the resulting function when you do that is just a minus sign in front of the sign. So you flip it, right? So this is what we call out of phase. And it's kind of like the two extreme cases. Like you can ask, okay, what happened if the phase difference is something in between? Well, we don't really have like a word for that. You can say that it's neither in phase nor out of phase. But most of the time we are not really worried about those cases because it's the extreme cases that we are mostly interested in. Okay, so the takeaway from this is that you can have two cases where the two waves are in phase, so they are exactly on top of each other, or they can be exactly out of phase, which is canceling out each other like this. So when you have two waves, like what do? You just add them. Okay, so that's what we call the superposition principle. And you're not gonna see this for this time only. You're gonna see the superposition principle again when we talk about electric field after midterm. Superposition principle is actually kind of more general concept that translates from mathematics. What it means is that if you have, in terms of, some of you might have studied, differential equations. And if you find the solution of the differential equation and you find the other solutions, so you have two solutions, when you add them, the new one is also a solution to the same differential equation, right? So that's kind of like the principle, superposition principle that we are talking about here. The thing is that we are talking about wave, so what we need to do is to find the solution to the wave equation, right? So you probably remember that we have some wave equation that looks something like this. Okay, so let me check if I got this correctly. No, I got this not correct. It's the other way around. Yeah, I should have checked the unit. Okay, anyway, so this is what we have in terms of the wave equation. So if we talk about wave, the wave has to satisfy this equation. But this equation is what we call in mathematics linear. Linear in this case does not mean it's a straight line. What it means is that if we have y1 to be a solution of this wave equation, and we have y2 which is different from y1, but y2 also solves this wave equation, you can come up with a new y3, which depends on x and t. But you can come up with y3 which is adding y1 and y2 together like this. And in this case, y3 is also a solution. I apologize for the noise coming from outside. Probably nothing I can do about that. Well, people have to earn money and do business, right? So I cannot just go out and say, go away because I'm teaching. So just bear with me for that thing. Well, okay, so this is what I mean by linear, okay? You can come up with a new solution by adding or combining the other solutions. And that's the kind of the underlying principle of the superposition principle, because if you have one wave and you have another wave, then you are sure, because of the what we call the linearity of the wave equation, that when you add the two waves together, the new wave is also a valid wave, because the new wave is the solution of the wave equation. So this is a little bit more technical, but I just want to show you that the superposition principle does not just pop up because someone says so, but it's a direct consequence of the linearity of the wave equation that we have here. And many topics or many fields in physics deal with linear set of equation. After the midterm, we're going to talk about electric field, magnetic field. Those are governed by what we call the Maxwell equations. Maxwell equation is also linear. Okay, so that means if you have a solution to the Maxwell equation, you have like electric field, you can add multiple electric field and it's still going to be a valid solution, right? So you can add one on top of each other, and that makes our life a lot easier than it's going to be otherwise. Right? So if you have like a nonlinear equation, then things will be very, very complicated. Anyway, for us, what it means is that, let's say we have one speaker giving out wave, and this wave is given by, let's say, y1 as a function of time and position, given by a sine kx minus omega t. And let's say magically we can overlap another speaker at exactly the same position, which is not impossible, right? Because I mean, how can two things be at the same place? But let's say we can do that, and it's also giving out wave, same frequency, same phase, same wavelength. So we have now y2, which is coming out from the red speaker, is also given by the same equation, same wave equation, wave function here. So the question is that if we are standing here and then listening to this wave, what would be the resulting wave? Well, according to the superposition principle, one is wave, the other one is wave. So when you add them, it's also a wave. So y, which is the resulting wave, is just a simple addition of the two. So just take y1 plus y2 like this. That's it. That's what we mean by superposition principle. So you're going to have a sine kx minus omega t plus a sine kx minus omega t. Same thing. So in the end, what I have is just twice of what I originally had, which is something like this, right? And the resulting wave is wave with the same frequency because omega didn't change. Same wavelength because k didn't change. Remember, k is the wave number, right? K is 2 pi divided by the wavelength lambda. So k gives you the information about the wavelength. So k didn't change. Omega also didn't change. So the frequency and the wavelength of the resulting wave is the same, are the same. The only thing which is different is the amplitude. The amplitude doubles. Okay, the amplitude doubles. And this is what we call constructive interference. And the reason why it's constructive, because when you add the two waves together, the phase difference are 0. Remember the phase difference, going back here. The phase difference are 0. That means they are in phase. That means when they go up together. When they come down together, right? So when you add them, they always add up. So you have what we call a constructive interference. Okay, so that should be something not that difficult to understand, hopefully. Now what I'm gonna do is I'm gonna put the red speaker at a different point. So I'm gonna leave the blue one the same. So the blue one gonna go coming out, the wave coming out gonna look like this. So sine wave again. But now the red one, I'm gonna place it exactly here. Okay, so move the red wave a little bit to the right. And I move it such that the distance that I move is exactly one wavelength. So the wave coming out from the red one still go up and down exactly at the same time as the blue one. So in terms of the wave function, y1 looks the same because we didn't change anything. A sine kx minus omega t. But strictly speaking, y2 is not the same, because what we do is we shift the wave of y2 to the right. So we have to minus something, right? Because shifting the graph to the right means you have to subtract something. And what do you subtract? Well, you subtract the variable that you are shifting. In this case, it's the x variable, right? So instead of writing minus phi there, I can just hide the minus phi into x here and write x minus the amount of the distance that I shift the graph. And in this case, I chose to shift the red one from the original position by exactly lambda. So what I put in for x here is x minus lambda, because I shift the whole graph by lambda, right, to the right. If I shift the whole graph to the left, then I would do x plus lambda. So in this case, x minus lambda. Okay, so that's gonna give me a sine k x minus lambda minus omega t. So if I multiply out, I have kx minus omega t, which is what I had earlier. But then the extra factor lambda here, I have minus k times lambda, right? And if you compare this to the original y2, right, compare these two together, right, the phase, additional phase that appear is this term here, k times lambda. That's the phase that I was about to put in the first place, but I say, okay, let's not do that, let's just put it in the x variable here. But it ends up giving the same effect, which is coming out to be some extra factor here. So you can see that what's the phase difference between y1 and y2 in this case? Remember, the phase difference is it's just the difference in the phase. For y1 is 0, for y2 is k lambda, okay? So in this case, when you add the two waves together, we're gonna do that later, but the phase difference, delta phi in this case is just, well, k times lambda. Well, don't worry about the minus sign in this point, because you can do phase of y2 minus phase of y1, or the other way around, y1 minus y2. It doesn't really make any difference. Okay, so maybe just to make sure that everyone understands, I just put absolute value here. Okay, so the phase difference is k times lambda, but what is k times lambda? Remember, k is 2 pi over lambda. So k times lambda is actually just 2 pi. But 2 pi and 0 are the same thing when you talk about sine and cosine function. Right? So in this case, it's as if the phase difference is 0. And you can see from this diagram already that the two wave goes up at the same times and then comes down at the same times. So they are in phase. Right? They are in phase. So strictly speaking, the two waves are in phase when delta phi is not just 0, but it can be also 2 pi, it can be 4 pi, it can be 6 pi. Actually, it can be anything which is multiple of 2 pi. So n times 2 pi, where n is an integer. And it's the same thing as, like sine of 0 is 0, sine of 360 degrees is also 0, sine of 720 degrees is also 0. So sine of multiple of 360 degrees or 2 pi is also 0. It's the same thing here, right? So if you do anything such that the phase difference of the two waves are 0, 2 pi, 4 pi, 6 pi, or something like this, right? That's going to give you in phase wave. Two waves going to be in phase, and they are going to be constructive interference, because when you add the two together, so y equal to y1 plus y2, right? So mathematically they are 2 pi away in terms of the phase. So kx minus omega t, and then plus a sine kx minus omega t minus 2 pi, okay? And mathematically sine of anything plus 2 pi or minus 2 pi is going to be the same. So the resulting wave is going to be 2a sine kx minus omega t. So still constructive interference. So what's the conclusion here? The conclusion is that if the two waves have the phase difference of 0, 2 pi, 4 pi, any multiple of 2 pi, then when you add that two waves together, they're going to interfere constructively, or we can call it constructive interference. So the wave amplitude is going to double. You're going to have larger waves. Now we're going to talk about the same thing, but from a little bit different perspective, right? Which I'm gonna use this to introduce the concept of path difference. Okay, what we are trying to do here is to figure out the phase difference in a different way. So let's talk about yourself as an observer. We can find the phase difference between the two waves by looking at the difference. Well, actually, it's probably better if I draw a new picture. So we have a blue speaker, and then we have a red speaker. So I should draw this first. Something like this, and then we have the red speaker, let's say here. So I shift the red speaker again to the right by one wavelength, so the wave coming out is still in phase, okay? Even though the phase difference is not exactly 0, it's 2 pi, but they are in phase by our definition. So our person is here. Let's call the blue one to be source number 1, and let's call the red one to be source number 2. And per convention, the observing point, which is where the person is, usually going to put the letter P here. I don't know why, but that's always what people use. The other way of finding the phase difference between the two waves is to look at the distance from P to the two sources. The first distance is from P to S1, so that's what we call the S1P distance. So that's going to be this distance here. The other one is S2P, which is from source 2 to the observing point P. Okay, so these two distances are kind of the parameter that depends on where the two speakers are. And we're going to define the thing which is called path difference. As you can guess from the name, path difference, or PD, is just the difference in the path from the source, the two sources, to the observing point P. So in this case, well, we're going to put an absolute sign because you can do one subtract by the other one. It doesn't really matter. So it's going to be the absolute sign of the distance P1 minus the distance S2P, not P1, S1P and S2P, like this. Okay, the path difference is the difference in the distance. So usually it has the unit of meter. Okay, so don't forget about this. Now, once you have the path difference, the phase difference is given by the ratio of the path difference to the wavelength times 2 pi. So it's PD divided by lambda times 2 pi. That's the phase difference. So this equation gives you the relation between the path difference and the phase difference between the two waves. So let's check whether this makes sense for our case. In this case, we move S2 to the right by 1 lambda, right? So that means S2P is shorter than S1P by 1 lambda. So in our case here, PD is absolute value of minus lambda. No, not minus sign because S1P is larger. So it's just lambda. So just lambda here. So the path difference is lambda. So that means the phase difference is lambda over lambda times 2 pi. So that means the phase difference is just 2 pi. So when the phase difference is 2 pi, you know that it's a constructive difference because of what we say in the earlier page. And you can see that this means that you can move S2 even further away and still get constructive interference as long as you move it such that the phase difference is a multiple of 2 pi. So how do you do that? Well, you just need to move the speaker by a multiple of lambda to get that, right? For example, you can do even further movement. Let's say you move the red one here, right? How much do you move? You move by 2 lambda. And the wave coming out is still in phase, right? So in this case, PD is 2 lambda. The phase difference is 2 lambda over lambda times 2 pi, so it's 4 pi, which is still multiple of 2 pi, so you still get constructive interference. Okay, so this is a very kind of, reliable way of figuring out if the two waves are gonna constructive interfere or not. So we can write down as a summary a condition for constructive interference And we're not going to have time to do the destructive interference, so that's what we're going to continue. By the way, I probably mentioned earlier that there's a makeup class this coming Saturday, right? So at 2 o'clock. I'm going to remind everyone again through Canvas system. If you can make it, so please show up. If not, then just wait for the video, right? I will try to post it as soon as possible. If you cannot make it, you have to watch the video before next Monday, okay? Because I'm going to continue the material. So I would assume by that time everyone would have watched the video, all right? So please be responsible for this, right? So this is kind of like a makeup of one of the holiday that we had earlier. And next week there's also another holiday on Wednesday. So for next week we're gonna have Monday class, and then we're gonna have another makeup on Saturday. Okay, so again, please check the announcement on Canvas again, just to make sure that you don't get the date and time wrong. Okay, anyway, before we finish today, let me just write down that the condition for constructive interference is this. First, so either one is fine because one gonna imply the other one. The path difference has to be a multiple of lambda. So n is gonna be integer always. N is any integer. So 0, 1, 2, 3, 4, 5. Right. So if you have the path difference to be a multiple of the wavelength, then the two waves gonna be constructive interference when you add the two together. So this also means that the phase difference is multiple of 2 pi, right? So PD, the phase difference is related to the path difference through this equation. Okay, so you can see that if this is true, then it implies that the other one must be true. Right, so either one is fine. You cannot have one true and the other one is not true, because that's gonna be contradicting this equation, and we shouldn't have that. Okay, so this is the condition for constructive interference. So in other words, if you want to see if the two waves gonna add up constructively or not, you look at either the phase. If you don't know the phase, then you might need to look at the path difference and figure out the phase difference that way. Okay. Anyway, we're going to continue our discussion on Saturday, and that's when we're going to talk about the destructive interference and maybe a little bit more about this to make sure that we understand everything. Okay. I think that's all I want to talk about for today. If you don't have any question, then I'll see some of you, or well, hopefully all of you, on Saturday. If not, then I'll see you all again on Monday. All right, so that's it for today. Take care and see you later.